Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 1 for January 2022. This is the Part 2 video. I'll put the link to the Part 1 video below in the description box. Let's begin with question 19. Question 19. This question is about the amount of water of crystallization in hydrated magnesium sulfate, which is that they say the value of X in the formula was determined in an experiment. The procedure is as below. In step 1, a crucible was weighed, a spatula measure of hydrated magnesium sulfate was added, and the crucible was reweighed. In step 2, the crucible containing the hydrated magnesium sulfate was heated using the apparatus shown. Here we see the sample, the crucible, and we see the heat. In step 3, after heating for 2 minutes, the crucible containing the magnesium sulfate was allowed to cool and was reweighed. They want you to complete the table of results. So the mass of the empty crucible was 21.21, and the mass of the crucible and the hydrated magnesium sulfate before heating was that. The mass of the crucible and magnesium sulfate after heating was that. So we can see that the mass of the water that is lost is going to be 26.71 minus 24.12, which is 2.59, as we can see here. And then they ask here, mass of magnesium sulfate after heating for 2 minutes. The mass of magnesium sulfate is going to be this, minus the mass of the crucible, which is 24.12 minus 21.21, which is 2.19. And of course for water, I've already told you, it's going to be this mass here, minus that mass, giving us 2.59. Moving on. Here they say, use these results to calculate the value of X in magnesium sulfate XH2O and give your answer to the nearest whole number. I wrote the equation that is going on. This is going to break down, giving us magnesium sulfate, and all the water will go away. Now from the table of results, the mass of magnesium sulfate was 2.91 and the mass of water was 2.59. We also know that the molar mass of magnesium sulfate is going to be 120.4 if you use this to calculate, and that for water is 18. So the number of moles is going to be that divided by that, and the number of moles here are going to be that divided by that. We got this and that as corresponding moles. To get the mole ratio, we divide through by the smallest number of moles. That divided by that gives us 1, and that divided by that gives us 5.9. Rounding off, it's going to be 1 to 6. Therefore, it should be 1 to x, which is 1 to 6, so x is equal to 6. Moving on. In part B, the correct value of X is greater than the value calculated in A2. Suggest a way of improving the method to obtain a more accurate result using the same apparatus and justify your answer. So here we need to heat to constant mass. Heat the hydrated sample to constant mass to ensure that all the water of crystallization is lost from the sample. So this brings us to the end of question 19. Let's continue to question 20. Question 20, this question is about copper and its compounds. Complete the electronic configuration of copper and copper 2+. Copper has the configuration argon 3d10 for S1. Because copper has 29 electrons, these are 18, so plus 11, that gives us 29. And then copper 2, it means it loses 2 electrons. One is going to be lost from the 4s and one is going to be lost from the 3d. So it's going to be for S0, 3d9, or you could just say argon, 3d9. In part B, a sample of copper contains the isotopes copper 63 and copper 65. They want you to complete the table to show the numbers of subatomic particles in atoms of these two isotopes of copper. So with copper 63, the number of protons, of course, are going to be 29 because copper has the atomic number 29. The neutrons are going to be 63 minus 29, which gives us 34. And the number of electrons are equal to the number of protons because this is an atom and not an ion. For copper 65, the same thing. Protons is 29 and electrons are 29, while the neutrons are 65 minus 29, giving us 36. The next part says, explain the term isotopes using the information in the table. From the table, isotopes have the same number of protons, they have the same number of electrons, but they have different number of neutrons. So moving down here, state why the two isotopes of copper have the same chemical reactions. Chemical reactions are determined by the number of electrons, more so valence electrons. So in this case, because they have the same electronic configuration or same number of valence electrons, so they have the same reaction. Moving on. The relative atomic mass of copper in this sample is 63.4. They wanted to calculate the percentage abundances of the isotopes, copper 63 and copper 65 in this sample, and you must show you're working clearly. If I let the percentage by mass of copper 63 to be x, that means the percentage by mass of copper 68 is going to be 100 minus x. So, x percent is going to be x over 100 times 63 plus the other percentage, which is 100 minus x, divide by 100 times 65, and that should give us the relative atomic mass, which is 63.4. So the rest is mathematics. We have 0.63x plus, this is going to be, of course, 1 minus 0.01x into 65. And to simplify and finding the value of x, I got x is equal to 80%. So 80% is going to be the percentage abundance of copper 63. It means 20% should be the percentage abundance of copper 65. Copper 2 sulfate can be made by reacting solid copper 2 carbonate with dilute sulfuric acid. They want you to write an equation for the reaction that occurs, and state symbols are not required. So this is copper carbonate reacting with sulfuric acid. Remember, when metal carbonates react with acids, we get salt, carbon dioxide, and water. The product is going to be copper sulfate, which is the salt, plus carbon dioxide, plus water, and everything is balanced. So this is the equation for the reaction. Here they say, an experiment was carried out to produce pure dry crystals of hydrated copper 2 sulfate, which is that. They say copper 2 carbonate was mixed with 50 centimeters cubed of 1 mole per decimeter cube sulfuric acid until no more reacted. So until no more reacted, it means the copper carbonate was in excess, and therefore sulfuric acid is going to be the limiting reagent. So we always use the moles of the limiting reagent to determine the moles of everything else that participated in the reaction, either that reacted or that was produced. The mass of hydrated copper sulfate obtained was 10.87. Calculate the percentage yield for this reaction, giving your answer to an appropriate number of significant figures. So I wrote some part of the equation. If we're getting hydrated copper 2 sulfate plus anything else, of course, that is not required, so I just left it like that. Volume here is 50 centimeters cubed, and the concentration is 1 mole per decimeter cubed. So moles of sulfuric acid is going to be concentration times volume, which is 1 times 50 divided by 1000. To convert that to decimeters cubed, it gave me 0.05 mole. And then I'm going to use the moles of this to find the moles of the product. So the ratio is 1:1, and that means the moles of the product, which is hydrated copper sulfate, are also going to be 0.05 mole. Now, when we go to the mass is always number of moles times the molar mass. We were given the molar mass here, so 0.05 times 249.6 gave me 12.48 grams. The percentage yield is actual yield divided by theoretical yield times 100. So in this case, the actual yield, of course, they told us 10.87, divided by my theoretical yield, which is 12.48, times 100, gave me about 87.1% as the percentage yield. So this brings us to the end of question 20. Let's continue to question 21. Question 21. This question is about alkenes. Alkenes contain a carbon-carbon double bond that consists of a sigma bond and a pi bond. They wanted to complete the diagram to show the areas of electron density for each bond and label the sigma and the pi bond. So of course, if this is the carbon-carbon double bond, we have a sigma bond as well as the pi bond. The pi bond, there is delocalization, so there is something above and below, and this is the pi bond, while this is going to be the sigma bond. Here they say propene is an alkene. The reagents needed for 3 reactions of propene are shown. So we can see here propene is reacted with steam in the presence of an acid catalyst to produce, of course, this acid catalyst is going to be phosphoric acid, and the alcohol is going to be produced, which is going to be this. Either the OH is going to be on this carbon or it will be on this carbon. However, I would expect it to be on carbon number 2 more, so this is going to be the main product, although that is also acceptable. Then in the next, they say reacting propene with acidified potassium manganate 7. This is an oxidizing agent, and a diO is going to be formed. So one OH group is going to be here and another on there while the double bond breaks away. So this is a diO. And when propane reacts with bromine, we're going to form 1,2-dibromopropane, which is going to be the product here, as the bromine comes here as well as there, and the double bond disappears. So moving on. Here they say, propene also reacts with hydrogen bromide. Give the mechanism for this reaction to form the major product and include Kali arrows and relevant lone pairs and dipoles. So hydrogen bromide, in this bond, we have a partial plus and a partial minus due to the electronegativity difference between Br and H. This bond breaks, forming a dative covalent bond between the carbon and this hydrogen, and then this bond breaks, leading to the formation of the bromide. However, because we are looking for the major product, it means the hydrogen is going to be attached here in order to form a secondary carbocation, as we can see here. This leads to formation of a major product. And then in the next step, a lone pair from Br minus is going to form a dative covalent bond onto the carbocation, forming this as our final product. In part C, alpha-ocimene contains 3 carbon-to-carbon double bonds. It is found in plants and has a sweet smell. The skeletal formula of alpha-ocimene is shown. If I can first remove away the carbons I placed so that you can see the structure, you can see this is the first carbon-carbon double bond, the second as well as the third. The first question asks us to give the molecular formula of alpha-ocimene. So to do that, I can take you back by placing my carbons there. So 1 carbon, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are 10 carbons. And here we have 2 hydrogens, 1 here, 3 here, 2 here, 1 there, 2 there, 3 here, and 2 here. And the total hydrogens are going to be 16. So that is the molecular formula. Moving on. Here they say, on the skeletal formula, draw a circle around the part of the molecule that gives rise to geometric isomerism of alpha-ocimene. If you look at this carbon here, there are 2 hydrogens here, so that is not a geometric isomer. There is no priority group. The same applies to this. However, here we have a higher priority here and a higher priority here while the hydrogen is there. So we can see this is going to be the carbon-carbon double bond that gives that structure geometric isomerism. Next they say, draw the skeletal formula of the other geometric isomer of alpha-ocimene. If you look at this structure, there is a hydrogen here. That means this is going to be the E isomer. So the other isomer we have to create, the higher priority groups have to be on the same side as we can see here. So the hydrogen is going to be here. And that means the structure should look like this. Here they say, in an experiment, 0.05 mole of alpha-ocimene reacted with 3.6 decimeters cubed of hydrogen in the presence of a catalyst. They want you to deduce the structure of the product of this reaction, and you must show your working clearly. They've also given us the molar volume of hydrogen is 24 decimeters cubed. I began by calculating the number of moles of hydrogen that reacted, which is going to be the volume of gas divided by the molar gas volume, and it gave me 0.15 mole. Then the mole ratio of alpha-ocimene to hydrogen is going to be 0.05 to 0.15 because we know this is given and we have calculated this. So the ratio finally becomes 1 to 3, which means 3 hydrogens reacted with 1 mole of alpha-ocimene. And that means all the 3 carbon-carbon double bonds became saturated. So the structure should be this, meaning all the double bonds disappear, and this is what is left. So this brings us to the end of question 21. Let's continue to question 22. Question 22. This question is about the bonding in the elements of period 3 of the periodic table. The melting temperatures of the period 3 elements are shown in the table. So they say, sodium, magnesium, and aluminium are metals. State what is meant by metallic bonding. Metallic bonding is the electrostatic attraction between cations and delocalized electrons. Next they say, melting temperature depends on the strength of the metallic bond. explain why the metallic bonding in magnesium is much stronger than that in sodium. If you compare magnesium and sodium, actually magnesium is smaller in size in comparison to sodium, yet magnesium has a higher charge. So it means magnesium loses more electrons to become Mg2+, and therefore it forms two metallic bonds in comparison to sodium. So I said magnesium loses 2 electrons to become Mg2+, while sodium loses 1 electron to become Na+. Magnesium 2+ has a higher charge than sodium+, and magnesium 2+ cation contains more protons than Na+, so Mg2+ has a smaller radius than Na. So Mg2+ attracts more electrons than Na+. Also, these electrons are attracted more strongly in Mg2+ than in Na. The stronger attraction is due to the smaller size and the more number of protons in the nucleus. Moving on. In the elements silicon, phosphorus, sulfur, and chlorine, the atoms are joined by covalent bonds. They want you to describe the attraction between atoms in covalent bonding. The attraction of atoms in a covalent bond is an electrostatic attraction between two nuclei and a pair of shared electrons. Next, they say, explain why the melting temperature of silicon is higher than that of phosphorus by referring to their structures. Now, silicon is a giant covalent structure, and silicon has multiple covalent bonds. When you melt silicon, we have to break these covalent bonds, and the process of breaking them or weakening them requires more energy in comparison to phosphorus, which is a simple molecule and it only has weak forces of attraction. These weak forces of attraction require less energy to be broken or to be weakened during the melting process. Moving on. In part C, they say, sulfur reacts with chlorine to form sulfur dichloride. Complete the dot and cross diagram of the molecule of sulfur dichloride and use dots for chlorine electrons and crosses for sulfur electrons. We can see chlorine has 7 electrons in the outer shell, plus 1 it shares with sulfur. And on the other side, sulfur has 6 electrons in the outer shell, plus 1 it shares each with chlorine. And then the other side, chlorine also has 7, plus 1 it shares with sulfur. So that should be the structure. Next, they say, suggest a value for the Cl-SCl bond angle and justify your answer. The bond angle is going to be 104.5. If you look at the structure, sulfur has 6 electrons in the outer shell. So 1, 2, 3, 4, 1 and 1 here. So those are 6 because this and that is a bond electron and each contributes 1. So because of these two lone pairs, there is going to be repulsion that creates the bend shape or the V shape. So this structure is going to be similar to that in water, and the bond angle is going to be 104.5. So I said the bond angle is 104.5. Sulfur has 2 lone pairs of electrons and it forms 2 bond pairs of electrons. The repulsion between lone pair is greater than that of lone pair bond pair, which is greater than that of bond pair. So the structure rearranges itself into a bent, or you would say V shape, to minimize repulsion. So this brings us to the end of question 22. Let's continue to question 23. Question 23. This question is about the ionization energies of the elements in period 2 of the periodic table. The first ionization energies of the period 2 elements are shown. So we can see the vertical axis has first ionization energy and the horizontal axis has element. We see from lithium to neon, there is a general trend that is increasing. They say give an equation that represents the first ionization energy of lithium, and they want you to include state symbols. So, because lithium is going to be gas when it's ionized, so lithium gas gives us lithium plus, which is a gas, plus 1 electron. In the next part, they want you to explain why there is a general increase in the first ionization energy across the period. Across the period, the number of protons are increasing because more electrons are added, however, to the same shell. And that means the inner shielding is almost the same. So if there is increase in the number of protons, that means there is increase in nuclear charge. So the increase in nuclear charge is going to be stronger than the tiny increase in the shielding, and therefore the size of the atoms are going to decrease. So I said, across the period, more protons are added, so the nuclear charge increases. However, the number of shells are not changed, So the effect from the increase in nuclear charge overcomes the shielding effect, and therefore there is greater attraction on valence electrons or outer shell electrons. Moving on. Explain why the first ionization energy of oxygen is lower than that of nitrogen. If you look at oxygen, the configuration is 1s2 2s2 2p4. In nitrogen, 1s2 2s2 2p3. So in oxygen, the first electron is taken away from an orbital where pairing has occurred, and in a paired orbital, there is going to be greater repulsion in comparison to here, where there are two p3 electrons, meaning each orbital has only one electron, so there is no repulsion within the orbital, and therefore I said in oxygen, the first electron is removed from a paired 2p orbital. Due to repulsion between the paired electrons, this energy is required to remove the electron. In nitrogen, the first electron is removed from an unpaired orbital, so more energy is going to be required. Next, they say, all the successive ionization energies of nitrogen are shown in the table. So they say, explain the trend in the successive ionization energies of nitrogen. We know nitrogen has 7 electrons, so these are going to be the inner 2, and then we have those others, 1, 2, 3, 4, 5, and then the 2 inside. So this is going to be the 1s2, 2s2, and the 2p3s. Between this and this is a tiny jump because all these electrons belong to the same shell. So this is moving from one subshell to the next subshell. However, there is a very big jump here because this is moving from the outer shell to the inner shell. We expect more energy is going to be required as electrons from inner shells are removed. So I said there is a general increase in ionization energy as more electrons are removed. And as more electrons are removed, repulsion decreases. Also, a slight jump between the third and the fourth is due to the removal of an electron from an inner orbital of the same shell. So a big jump between the fifth and the sixth ionization energy is because the sixth electron is removed from an inner shell. So this brings us to the end of question 23. Let's continue to question 24. Question 24. They say a 0.21 gram sample of a volatile organic liquid C is injected into a gas syringe and heated in an oven. At 100 kilopascals and 358 Kelvin, the syringe contains 72.5 centimeters cubed of gas. They say calculate the molar mass of C. I use the formula PV is equal to nRT. So if PV is nRT, when I have the pressure is given to me, it's 100 kilopascals, you convert that to pascals. Temperature is given as 358. The volume is given as 72.5 centimeters cubed, but we have to convert that to meters cubed. So I multiply by 10 power negative 6, which gave me that. The mass is also given as 0.210 grams. So it means if I have the mass, I can convert number of moles as mass over molar mass and make molar mass the subject, which gives me molar mass is equal to mass times R times T divided by PV. Now that I have this formula, I can substitute everything as you see here. So MR will be 0.21 times 8.31, which is the value for R, times 358, which is the value for T, divided by the pressure times the volume. And when I simplified, I got 86.171, which is about 86 grams per mole. Down here they say, the organic liquid C is a hydrocarbon. Give a possible name or formula for C using your answer. I use this molecular mass to find out which hydrocarbon it corresponds to. And of course, this has to be trial and error. I began by dividing this by 12 to see the approximation, and it gave me about 7. So it means if I go down to 6 carbons, does it make 14 hydrogens? And of course, that happened. And so the formula I got was carbon 6, hydrogen 14. So that was my answer. So this brings us to the end of this video as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.